Okay, quickly let's review for the Unit 9 exam. And first thing I want you to understand is what thermal energy is. Thermal energy is the energy contained in molecules and atoms as they vibrate with respect to each other. And maybe you have a solid, like a whole array of these each little dot here might represent an atom in some solid, like a crystal or something like that. And the little lines in between represent the bonds between them, and the bonds are kind of like little springs. So if you have two atoms that are connected by a bond and they stretch out, maybe they're moving apart from each other, they have kinetic energy because they're in motion, but they also have it's kind of like elastic potential energy. It's their energy due to their position with each other. They might attract each other if you try to pull them too far apart, but they'll repel each other if you try to put them too close. And so there's energy stored in that. And the energy that a material has, because the atoms and molecules are vibrating like that, and thus having kinetic energy and potential energy with respect to each other, that's called thermal energy. And remember, energy is the capacity to make change in your environment. So if something is really, 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 really hot, compared to something else, like hot boiling water compared to your hand, you stick your hand in that water, change is going to happen. So that's thermal energy. Thermal energy is the energy contained in an object because it has temperature. And that's really what we're measuring when we measure temperature is, it's a value that describes how these objects are vibrating with respect to each other. So something that's really, really hot, the atoms are vibrating very, very fast. They're moving high kinetic energies, or they have a lot of elastic energy between them, if they're bouncing off each other or something like that. So that's thermal energy. Now, one of the most important ideas in physics, well, there's two. There's conservation of energy. And here's the thing, in thermodynamics, or in any closed process in nature, energy is conserved. We cannot create energy from nothing, and we can't destroy energy. Energy just exists. We can change the way it exists within nature, but we can't change the amount of it. We can change the amount of a certain type of energy, but that energy has to be turned into a different way of existing. And so it still exists in the universe. The second, and this is the first law of thermodynamics, conservation of energy. Energy cannot be created or destroyed. The second law is a little more subtle, but also it just makes total sense. The second law says that the transfer of thermal energy, which we call heat, which is the transfer of thermal energy, and we use the letter Q to represent heat. I don't know why, we just do. Well, heat always flows from what to what? From high to low, what? High to low temperature. Always, always, always. And this idea, and it's simple, right? I mean, if I have, it's empty. But if I have, a cup of coffee and it's really, really hot, I know that the coffee is going to get cooler and until it reaches the same temperature as the environment around it. Heat will flow from high to low. I'll never have a situation where if I have a hot cup of coffee and I'm in a normal room, and that hot coffee will never get hotter at the expense of the room getting colder. Now, the coffee getting hotter at the expense of the room getting colder does not violate the first law. Energy is conserved. But it does violate the second law. And the second law is a law. Okay? You cannot make heat flow uphill. You cannot you can't create any process that ends up extracting more heat, more thermal energy from low temperature and depositing it to high temperature. You might say, well, what about a refrigerator? A refrigerator does not violate the second law. It does reverse the flow of heat in a way, but at the expense of the rest of the universe. So we'll talk a little bit more about that when we talk about heat engines. But the second law, heat always flows from high to low. And so what we have is the classic thought experiment. You have an ice chest, and then you put some cellophane in there. And over here, you dump some boiling hot water. Maybe it's at 98 degrees Celsius. And then over here, you dump some ice water. But you have like aluminum foil or cellophane or something separating them so they can't just mix. And this is at 0 degrees Celsius. What do we know is going to happen if we wait a while? We know that they're going to reach the same temperature. If I stick in a thermometer and I watch the temperature of this guy, stick in a thermometer, watch the temperature of this guy is going to get colder. This guy's going to get warmer until they reach what? The same temperature. So thermal energy is going to flow, which we call heat. It's going to flow from high to low temperature. And so let's call this A and this B. Okay? What we know is that the heat that flows out of A plus the heat that flows into B will be equal to 0. What is this a statement of? The first law, conservation of energy. Just as much heat will flow out of A as flows into B, and until they reach the same final temperature. Okay? So the first law basically says this, well, the heat lost from A will be equal to negative heat gained by B. So this is thermal energy lost from A will be equal to the negative of the heat gained from B. Okay, you're just transferring thermal energy from this guy into this guy. You have the total amount of energy doesn't change. You're just transferring it from one thing into another. That's the first law. And the fact that it will go from the high to the low temperature thing, that's an application of the second law. This describes so much of what we observe about our universe. It describes the ultimate fate of our universe. It also talks about maybe how we define time. You know, we say time flows because heat flows from high to low temperature. It doesn't get bigger than that, these ideas. Well, then we have, well, what is the effect on materials if you add heat or take heat away? So heating, okay, if I have a material, maybe a liquid, and I put it on a hot plate, turn the little knob, turn the heat up, heat will flow from the hot plate into the water, and it will raise its temperature. And so the amount of heat that I add will cause this temperature to increase. So that is a change in temperature. Now the amount of temperature change also depends on how much mass I have. If I have twice as much water, to raise the temperature, I got to put in twice as much heat. So the amount of heat I need is directly proportional to the mass. Now, how much heat I need to raise the temperature of a certain quantity of this stuff by a certain temperature change, well, that's a property of that material, and that's called the specific heat capacity. Now, if you can't remember how to write the definition for the specific heat capacity, just remember this equation, and you can solve for it. C equals Q over M delta T. So it's the amount of heat you need per kilogram of mass to raise the temperature by 1 degree Celsius, or whatever units you're going to use. So this formula kind of defines what it is. Now you're going to have to be able to define specific heat capacity on the test. I expect you to know what it means. What is specific heat capacity for any material? Well, this is what you get when you are changing the temperature of an object. But you can also add heat and not see a temperature change if you're going through a phase change. For example, if I have my beaker like this, and I got a bunch of ice cubes in there, and I put this on a hot plate, and I got heat flowing from high to low temperature. But if I have a stick a thermometer in there, I don't notice a temperature change. Why is that? Because the heat is not changing the temperature of the water, it's instead melting the ice. And it takes energy to do that. If you look at water molecules, they're all lined up in a nice, neat little stack. They all have bonds, and I'm not sure I'm drawing a, I don't think this is the right alignment of water molecules, but it's just a nice, neat array. When you add heat to it, instead of raising the temperature, instead of making them jiggle faster, it breaks the bonds between them, and it melts them. And so that takes energy. And so the amount of energy it takes to melt an object, you have to put heat into it to melt it, and that's, well, you know, twice the mass takes twice the amount of heat to melt something. That's the heat of, heat of fusion. Now, I don't know why they call it the heat of fusion. Maybe you can look it up and tell me. I don't really care, actually. But this is a property of the material. Now, by the way, on the test, do you have to memorize the specific heat, the heat of fusion, the heat of vaporization of any material? No, you don't have to memorize it. I will give you a little table on the test that has everything you need to solve the problem. Specific heat capacities, heat, and this is the heat of fusion. And then, of course, if you make this hot enough, there's the same beaker, there's water in it. Put it on a hot plate. My hot plates are getting sloppier. But now you're getting little bubbles coming up here, and they're popping and going off. What are we doing? We are boiling the water. We are vaporizing it. So now the heat that's being transferred is not changing the temperature. Instead, it's vaporizing the liquid. So here Q equals the mass of the liquid that we want to vaporize times the heat of vaporization. So there will be a problem on the test where you have to take a solid and you have to raise its temperature until it starts to melt. So you would use this. And then you melt it. How much heat does that take? Well, you would use this. Then we're going to raise the temperature again to its boiling point. Well, then you would use this again. But now instead of for ice, you would use it for water. And then you're going to boil it away. If you boil it away, you have to use this. Now, of course, we can go in reverse. If I extract, let's say I have water vapor floating around in the air. Well, and I have a cold drink or something, and I notice little beads of water forming on the side of the drink. That is water vapor condensing, or going through the opposite of this. It extracts heat from it. And when you extract heat from it, it will change state from a gas to a liquid. And then you'll lower its temperature. You have to extract heat to lower its temperature. Then you can actually freeze it. Have you ever had a mug or something you put in the freezer and then it actually will form frost on your mug? Have you ever seen that? Okay. There's a certain beverage that I don't feel it would be professionally appropriate for me to mention but I like to drink it in the summer quite cold. So I actually have this big mug and I put it in the freezer. It has a fluid in it that freezes. I pour this particular beverage into it and it keeps it cold. But then I notice that on the outside of it, frost starts to form. Where did that frost come from? It came from water vapor. It condensed into a liquid. So you had to extract heat from it. You had to lower its temperature, and then you had to freeze it. And all that heat went into the mug. And so, eventually the mug will warm up. But so these processes go in two directions. If I add heat to a system, we call that positive Q. But if the heat radiates away, it comes out of something, we call it negative Q, negative heat. Okay. So you'll have problems where you have to use these. Okay? So just work, we've done a bunch of them, so review them. Not going to work a bunch of problems here. Then on the test, I want you to be able to describe what a heat engine is. You have some high temperature stuff. Just anything that's at a higher temperature. Burning gasoline. Fissioning uranium. I don't know. Anything that's really, really hot. Geothermal power. You put water underground, it gets really, really hot. From radioactive decay in the ground, heats up the water, bring that hot water up, flash it to steam, you put it through some kind of machine. This machine is so hard to draw that we just make it a circle. Heat flows out of the high temperature. This is in joules, right? Heat comes out of the high temperature, and we have some device that magically turns it into work, mechanical work. That's what we did with those aluminum cans when we made the aluminum cans spin. If you weren't here last time, I'm sorry. You missed it. We made aluminum cans spin really, really fast. That was mechanical work. But heat is still going to flow into a low temperature reservoir. And this is called QL. Now the first law of thermodynamics says this: the energy that flows into my heat engine must be equal to the energy that flows out in order to conserve energy. So the heat that flows out will be equal to the heat that flows into it will be equal to the heat that flows out of it, and the work. Now efficiency. I want you to be able to calculate the efficiency of an engine. The efficiency of an engine, which I'll call it E for efficiency, is equal to the work you get out of it divided by the heat that flowed into it. So if you want to know what the efficiency of a heat engine is, just how much mechanical work do I get out, how much heat flowed into it. It will always be less, always will be less than 100%. Well, you have to make this a percentage, you have to multiply it by 100%, right? It's always less than, as a decimal, it's always less than 1. In other words, the work you get out of it always has to be less than the heat that went into it. Why? Because there always will be some heat flowing into the low temperature reservoir. You have to. Because, heat flows from high to low temperature. Well, if heat isn't flowing into a low temperature, there's no reason for it to flow. And you would be violating all kinds of laws, and you would be violating this idea of entropy. Okay. So, be able to calculate the efficiency of a heat engine. Also, some vocabulary. you need to know. Entropy. You see, the universe is running itself down. Entropy is increasing. Entropy is a measure of the disorganization of the universe. And look, here's one way to think about it. If I took my high temperature stuff that I had before, here's high temperature stuff and here's low temperature stuff. So these molecules are moving really, really fast. These molecules are moving really slow. This, in so many ways, is a very unlikely occurrence, isn't it? It's very organized. All the high temperature molecules are over here. All the low temperature molecules are over here. Well, if you wait a long time, as Q flows out of the high into the low temperature, they're going to even out, and it's just going to be a big disorganized mess. It's all going to be the same, all going to be run down. It's going to reach the same final temperature, and that's entropy. We did define a change in entropy as being the heat that flows divided by the temperature in kelvins, but not a big deal. This is actually not going to be on the test. Finally, last vocabulary, and the bell's going to ring in about 3 minutes, so I need to hurry this up. Heat flows in one of 3 ways. You need to describe these 3 ways: conduction, convection, and radiation. They're in your book. Look them up and be prepared to explain what they are. If you grab a frying pan on a stove with your hand and it burns your hand, you just got burned. Heat flowed into your hand through conduction. That's direct contact. Convection, that's like what happens in boiling water. Hot water comes up and then it sinks down when it cools off. You get a roiling boil kind of a thing. That's convection. This is through the motion of fluids, and fluids can be gases as well as liquids. Radiation, that's when it's not moving through material, it's moving through photons. When you put your hand over, like up to a campfire, or when you feel the warmth of the sun on your face, that's heat flowing from the high temperature surface of the sun to the low temperature of your face through photons, through electromagnetic radiation. And that anything that has a temperature higher than its environment will radiate heat into that environment through radiation. So memorize that. I think that if you understand how to do all this stuff, you're going to do very, very, very well on the test. So good luck. That is all.